Okay, after that stunning introduction to the equation of the straight line in its various forms, let's move on to something which isn't a straight line, the circle. So we're going to look at essentially two different forms for the equation of a circle and properties of the circle, again all of which you are likely to be familiar with in one shape or form. So the first equation of the circle that you meet is that which is centered at the origin 0, 0 and radius r, and obviously the definition of a circle is the locus of all points which are equidistant, so a fixed constant distance from a fixed point. In this case, if that fixed point is the origin, then if the fixed distance is r, one traces out a circle as shown. Now, in order to write down the equation for the circle, you just need to define P to be a point on the circle with general coordinates x, y as shown, and then of course in this right angle triangle we know that the hypotenuse squared, which is r squared, is the sum of the squares of the other two sides from Pythagoras' theorem. In other words, the xy coordinates satisfy x squared plus y squared is r squared. Okay, that's a relationship between the x and y coordinates of any point on the locus, and hence that's the equation of the circle. Okay, what happens now if the circle isn't centered on the origin? Well, that's not difficult to determine because everything is just shifted. So here, to generalize that result, this circle has center PQ, radius r again, and a point P on that circumference with coordinates x, y, again satisfies the Pythagoras' theorem in this right angle triangle, but in this case, whilst the hypotenuse squared is still r squared, clearly the length of the adjacent and opposite sides are not x and y, they're going to be x minus p and y minus q. In other words, the sum of the squares of those two distances will be r squared, and this time we get this equation. So that's the general equation of a circle, centre P, Q, radius r. Now, there is one more general form for the equation of a circle, which is in an expanded quadratic form. We won't use this very often, but it's important to recognise that when one has a general quadratic expression, whether it's a circle or not, and indeed later on we'll see that they're not always circles. So how do we get to a general form for a circle? Well, if we take the equation of the circle that we've just seen, for which we know the centre PQ and the radius r, if we expand that out, we get this general quadratic expression. Now, in the same way that a general linear expression represents a straight line, a general quadratic expression of this form could represent a circle, but it doesn't necessarily have to represent a circle. In this case, it clearly is a circle because it started off as equation 1, which has been expanded. But if we look at this expression here, we see terms involving x squared, y squared, x, y, and then a constant. And so if we write down a general expression which involves just x squareds, y squareds, a multiple of x, a multiple of y, and a constant, then 2 looks very much like this expression here. In particular, I force the coefficients of x squared and y squared both to be 1, as I have up here. And for convenience, I've kept in the 2. As you'll see in a moment, it makes it a lot easier when one completes the square. So the general circle as described here can be rewritten like this, which makes us think that an equation of this form with just x squared, plus y squared plus a multiple of x plus a multiple of y plus a constant being 0 could represent a circle. I've called this 2 times some general number f, 2 times some general number g, and then some constant c. Remember, the 2 is there to make it easier to complete the square. So let's suppose we were just presented with equation 2. What could we deduce from it? Well, clearly we can complete the square, which I've done in going from 2 to 3. So this is already twice fx, so I can put that in one go in here. If I'd called that just fx, I'd have to have a half in here, so that's not terribly convenient. So the x squared plus 2fx can be replaced by x plus f all squared minus f squared, but I've put that on the other side. And similarly, y squared plus 2gy can be replaced by y plus g all squared minus g squared, which I've put on the other side, and I've also put the c on the other side. Now, when we look at equation 3, we can see that looks very much like equation 1. In other words, equation 3, which is the same as equation 2 being a general quadratic expression in x, y, x squared, y squared, where the coefficients of x squared and y squared are both 1, is a circle whose centre is going to be minus f minus g with radius the square root of this. But of course, if this quantity here is 0 or negative, then there is no radius. It's either 0, for which it just represents a point, or it's negative, for which the square root of this expression is not real and there is no circle. So in other words, equation 2, which can be rewritten as equation 3, represents a circle with centre minus f minus g, where these are f and g, radius the square root of f squared plus g squared minus c, determined by these numbers, provided that expression is positive. If this expression is 0, this is just 0, and there's only one point on the locus, which is the centre of a circle with 0 radius, minus f comma minus g. If this expression here is negative, there is no circle. There are no points on this locus, or this one. There are no values of x and y which satisfy that expression. Now, some of the curves that we will look at later on are much more conveniently described in terms of a parameter. So just to introduce the idea of a parametric form, which will be familiar to you, particularly in calculus, rather than relating x and y through some Cartesian equation, instead one can pick a single parameter which, when varied, represents all points on the locus. And in this particular case, on the circle, centre the origin, radius r, if I denote the parameter theta to be the angle that the line segment O to P for a general point P makes with the x-axis, then as theta changes, obviously xy changes. And in particular, just from this triangle, x is r cos theta and y is r sin theta. And as theta varies from 0 to 2 pi in radians, the whole circle is traced out. Now this expression here represents the parametric form for the equation of a circle, radius r, centre the origin, where theta is now the parameter, and if I vary theta between 0 and 2 pi, then all of these points will be traced out on this circle. So this parametric form is different from the Cartesian form. The variable theta parameter traces out all of the points. One can do exactly the same thing for a circle which isn't centred on the origin, so in this particular instance my circle is centre PQ, still radius R, and in this case from this triangle with theta being the parameter, then x minus p will be r cos theta. In other words, x is going to be the distance p plus r cos theta, and similarly y is q plus r sine theta. If p and q are both 0, c is at the origin and we get what we had before. So that's the Cartesian equation of a circle, centre PQ, radius r, where theta is the parameter. Now we move on to tangents and normals. A tangent is a straight line which just touches a curve at one point. Similarly, a normal will be a curve which crosses at a tangent at right angles. So we will determine tangents and normals to a circle, which is relatively easy, and then we'll go on to look at tangents and normals to a whole series of other curves later on.